This video is one of a series of videos about the marching cubes algorithm that calculates an isosurface from volume data. In a previous video, we wrote a basic Python function that implements the marching cubes algorithm. In this video, we will look at the performance of that function and consider ways to convert certain operations to leverage the powerful methods of NumPy arrays, including advanced slicing and filtering that can be used to significantly speed up code execution. To recap, volume data is a set of values distributed evenly across an n-dimensional space, sometimes also called voxel data. And an isosurface is a geometric shape that separates the values according to whether they are above or below a certain level. The surface is made up of triangles that connect vertices that are interpolated to be at the position within the volume where the value equals the level. In a previous video, we wrote a marching basic.py basic implementation of the marching cubes algorithm. We defined a function called marching that took a volume and level as arguments. The isosurface would be defined by a list of vertices, 3-dimensional coordinates, and a list of triangles, sets of 3 integers referring to the index of a vertex within the vertices list. The algorithm started by comparing everything in the volume with respect to the supplied level, resulting in a Boolean array that we called volume test. Then we enumerated every single point within the volume's 3 x, y, and z coordinates. We looked to see where the volume crossed the level of the isosurface by comparing adjacent values in the volume test. And where these were different, we calculated a delta by passing the values of the volume at those positions into a linear interpolation function, and that allowed us to create a vertex which we appended to the vertices list. We also created a vertex ID, a unique ID for each vertex that depended upon the x, y, and z coordinates, as well as the direction of the axis that we were looking along to find the vertex. To find the geometry, first of all, we considered a unit cube defined by its corners at x, y, and z, and x plus 1, y plus 1, and z plus 1. And depending on the value of the volume test at each corner, we assigned one of 2 to the power 8 types that ranged between 0 and 255. Then we used that type to look up the requisite geometry from a predefined lookup table that contains solutions for all 256 cases of volume type. This geometry took the form of edge information that could be converted to vertex IDs. Finally, we converted these unique vertex IDs, which are custom to the volume, to be ordered indexes of each vertex within a vertex list. This could be returned to various geometry drawing packages, and we showed this done in Blender. We analysed some test data that the result of caffeine molecular orbital calculations, and our function worked well to give the desired results, which was an easy to visualise isosurface. This output was the same as that from the scikit image or skimage package that has a skimage.measure.marchingcubes function. In this video, we're going to see how long our code took to run and if we can improve it. So to start with, previously we looked at the level at several different levels, but it's best here if we just stick to 1, so we'll do 0.05. That gives us nice results for this data. We'll unindent the code, and we also don't need to save the output, so we can delete this section. And we were going to group the different parts of the code according to whether it was our version or Skimmage, just to tidy things up a little bit. So if we switch to the terminal and run the program, we can see a noticeable delay before the code has finished and returns the result. Now we can quantify that delay by using the Unix shell time command. That if you're in Windows, an equivalent would be to use PowerShell's measure command. And on my computer, this shows that the program takes between 4 and 5 seconds to return its result. If we go to the code, and maybe we can comment out the scikit image part of the program, and running this again, we can see, well, it takes almost exactly the same amount of time. So it suggests that it's our function which is slow, especially when it's compared to the one implemented in scikit image. Well, we could go through and comment out various parts of our code and have some kind of spreadsheet of tabulated values, but this becomes very complicated very quickly. So a much better way to analyze the code's performance is to profile it. So we will define a function called profile that will take a target, and we are going to use one of the Python built-in recommended profilers which we'll import, and that is called cProfile. And cProfile has a function called run that will just take our target as a parameter. Now, to run this code, we will enclose the part of the program we want to analyze in triple quotes, and we'll send that as the target to our profile function. If we do this, we can see a lot of information as the result. Now, because I'm trying to make a video here, in the interest of fitting the information that we need on the screen, I'm going to modify our profile function slightly. So I'm going to import temp file and pstats. That allows us to interact with the output from cProfile. And first of all, we'll create a temp_file that will be a temp file.named temporary file. And we'll pass that temp file in as the second parameter of the run cProfile.run function. Now we can load the stats, and we'll call that p by creating a pstats.stats object and using the temp file as the argument. Both of these need to be the temp file.name, sorry. And to make the stats look nice, we can call the p.stripders method and then sort them according to pstats.sortkey.nfl. And that sorts them by function name. And then finally, we can output them using p.printstats. You can still see there's quite a lot of information here. So what we can do is finally filter this according to arching, which will match things that contain arching. So either with a capital or lowercase m. And now we can see just a small amount of information, which is a little bit easier to fit on this video. Looking at the information, we can see that all it's telling us right now is that we have one function that's called marching that takes over 99% of the time. And because we only really did everything within one function, we can't really see specifically what took the time. However, we can see that profile does split everything into function calls. So simply, to get more information, we can add more functions. And the easiest way to do this is to enclose our code in functions. So starting with finding the vertices, we can define find vertices function, and we'll define this in place. So we'll indent the code, and then obviously we need to call the function, but here we don't need to pass any parameters or receive any results, because defining the function in place means that it has access to all of the values as defined, and this function only acts upon Python lists, which are mutable, and it only changes them in place, so therefore we don't need to return them. We can do the same thing for the volume type calculation, so we can define calculate volume type. We can place all the code indented block underneath. Now this time we do have volume type that we need to return, so let's return that at the bottom. And we will collect that variable as we call the new function. We can repeat this process for looking up the geometry. So we'll define lookup geometry. Again, we don't need any parameters or arguments because it's defined in place. And we're also not acting on anything other than changing lists in place, so we can just call the function without collecting any return arguments. And finally, we'll do the same thing for converting the IDs to indexes. Again, this only alters lists in place, so we can just call it directly. And now we have all of the different parts of our function enclosed in other function definitions. Now, when we analyze the function with cProfile, the first thing to note is that the overall thing is significantly slower. And that is because we've got the significant overhead of over 2 million additional functional calls. Now, it turns out in this case that the overhead of this is negligible according to some of the other things that we're looking at, but it's really important to remember this as we proceed. Most importantly though, we can see that the different function calls have been nicely summarized in the output. Around about half of the marching function call is spent finding vertices, with around about 30% spent looking up geometry, and about 14% calculating volume type. So it really does look like all of the parts of our function contribute to the long execution of the program. And how may we go about improving this situation? Well, first of all, it's not really all that bad. If you really just want to call this function a few times on relatively small data sets, then you can just wait. We are about 14 minutes into this video, so we could have run the program over 160 times. But if you want to evaluate this isosurface at a range of different levels for different data sets, for example, in molecular orbitals, you might want to look at all of the different molecular orbitals at a few different levels, or for scientific data or medical data from an MRI machine, maybe you even want to watch this time over time. Well, then you're going to have to run this program many times, and we need some optimization. Well, we could just buy a faster computer. Now, this computer's already pretty good, thank you very much, and even with the very fastest CPUs, this code won't run very much faster. If we look at the marching cubes algorithm, and this is discussed in the previous video, the key feature is that it really doesn't matter the order in which we do any of the evaluations within the volume. So it's very easy to split this program into small packages, send it off to different CPU cores or even different computers. Now, there's actually significant overhead in doing this. So this is not the best option at this stage within this program. We could just abandon ship and not do any of this in Python. If you look at implementations of marching cubes, you'll find many different ones in C or C++ or similar low-level languages, which are much faster. The code is the same as the code we wrote in Python, going through the volume and looking at things like we did. But Python has massive overheads when doing things like enumerating loops and creating variables. And these overheads which make it such a great language to interact with, but it can lead to much slower code. The option which we're going to start exploring is to stay in Python but leverage the very powerful features in NumPy, a package that is specifically designed for efficiently processing large multi-dimensional arrays like volume data. This is the combined benefit that we can stay within beloved Python, but leverage the very efficient code written by the experts that contributed to NumPy. And in many cases, this code is running in low-level languages. So overall, this video is not only about improving this marching cubes algorithm, but also showcasing some of the advanced NumPy slicing and filtering methods. The first target for conversion to NumPy methods is to calculate the volume type. Now, this wasn't the most time-consuming part of our program, but it's the easiest place to start, so let's go. To replicate this calculation, what we can simply do is we'll copy the code that we had previously, but now we're not going to do this within the loop, so we can put this in a new location before the loop. And we'll just fix the indentation, and we'll call this calculate volume types with an S, and we'll collect the appropriate return value. Now, before, the first step was to initialize volume type to be 0. And we need to do the exact same thing again, but this time over the whole volume. So we can call volume types a numpy.zeros function, that will create an array full of zeros with a shape given by its arguments. Now, what we want is an array which is 1 less than the size of the volume test, remembering that we need to define our unit cube that we're considering by x, y, and z, and then 1 step in each of the directions. So that means we can't go up to the very edge, and we need to stop 1 step before the end. And we can get this number by creating a tuple of n-1 for n in each of the volume test dot shape. And because the total number of volume types is Boolean, which gives us 2 to the power of 8, which is the number of corners, that's 256, which fits inside an unsigned 8-bit integer. So we can let NumPy know this by adding this to the D type. Okay, so what we did previously was we did a bitwise OR with a unique value, which we started off as 1, to get our volume type. And NumPy has a bitwise OR function, which we can use. And we can pass it our volume types, and then the value in which we want to do the bitwise OR with, which will start off with 1, which is 1 shifted 0 times. And then we want to save this output back into volume types. And we don't want to do this over the whole array, otherwise we'll end up with a volume type of 255 for every single case. And so we only want to do this where the volume test is true at x, y, and z. And we can specify this using the where keyword argument. We can't, however, use our x, y, and z variables because outside of that loop, they don't mean anything. We need a way to tell NumPy to do this at the equivalent of the x, y, and z positions, but across the whole array. And we're going to use slicing to do that. To reference all of the values in an array along a particular axis, then we can write a colon. And the colon is equivalent to a slice object of none, none, and none, which means it starts at the 0th element, stops at the last element, and takes single steps along the way. So this will give us the value of volume test at every single position across every single axis. However, we've got to remember that our volume type's size is 1 smaller in every dimension than volume test. So to make the data fit, what we'll need to do is stop just before the end of the axis. So we'll slice up until -1, so by writing colon -1 for each of the 3 axes. And now we've done that for the first one, we can copy and paste that to the second one. This time we had 1 bit shifted once, which is number 2. And we had to look in the x plus 1 location. Now with slicing, we can achieve this by, instead of starting at 0, we'll start at 1. So we'll start 1 position shifted along the x-axis. And now, of course, we don't need to stop early. We can write 1 colon. Now for the third case, with 1 shifted twice, we want x plus 1 and y plus 1. So we can change y to 1 colon. And then in the next step along our cube's corners, we want 1 shifted 3 times. And now we only want to look in y plus 1. So we need to slice x up until -1, and we can keep y as 1 colon. So this is the 4 bottom corners of our unit cube, and the 4 top corners are repeated in the same order, but with z plus 1 in every case. So we can copy these 4, paste them, and then change each of the third axis slices to be 1 colon instead of colon 2 -1. We also need to change our shifts to 4, 5, 6, and 7. We can delete all that code, and we need to return volume types. So if we now jump to within our loop where we calculated the volume type previously, we can compare the 2 different versions. So if we write assert volume type equals double equals volume type at the x, y, and z position. Now this should be the same. The volume type we calculate in the loop should be the same as the x, y, and z position within the array of volume types that we calculated. And if it's not, it will cause an error. So if we run the program, well, it finishes with no errors, which means that all of our volume types calculations match. And more importantly, though, we can look at our profiling output. And we can see that we have a massive improvement with the NumPy methods approach seeming to be 700 times faster than what we had before. It's not entirely fair because obviously our calculate volume type does include almost 700,000 calls to a function, whereas there's only one calculate volume types call. But we can consider that negligible. On this computer, that many function calls probably takes around about 5/100ths of a second. So compare with the 7/10ths of a second, it is negligible. And there we go. Simply by changing the operations from Python to NumPy methods, we have a significant speed up within this function. And now we've seen that we can do this, what we can do is go back and look at the other parts of our marching function and see if we can get the same kind of speed up.